Good morning. I'm Donggyu from Seoul National University. Today I'll show how our novel system Empilo makes truly immersive 3D video conferencing possible on mobile devices by sending compact parameters instead of bandwidth-demanding visual data, and show how it still hits the strict latency budget of real-time communications. Let's start with a quick definition. On the left, we have what most of us use every day, 2D video-based communication. A single camera captures and streams a video, and everyone receives exactly the same frames. Moving from the legacy, on the right is our target, 3D video-based communication. Here, each participant is captured as a full 3D representation, so the viewers can choose any viewpoint as if they were talking to each other in person. But this extra realism comes at a cost. In fact, we encounter the key challenge. That is, how do we tame the exploding demand for network bandwidth and on-device communication? Of course, there have been multiple efforts to 3D video communication so far, and they show why mobile immersion remains inaccessible. First, you see Google's trajectory from Project Starline to the newer one, Google Beam. These systems offer breathtaking life-size 3D presence, but they work only in a fixed studio setting with multiple cameras and sensors. On the other hand, academic research such as far-fetched fusion has made the system fully mobile end-to-end, but it still relies on 3 cameras at the center. The pattern is clear. Today's systems depend on bulky multi-camera settings, so none can run in the single selfie cam on your smartphone. Our system, Empilo, aims to break that hardware barrier, enabling 3D experience with nothing more than a single smartphone. In this context, neural radiance fields, or so-called as NERF, let us generate any new viewpoint of the subject that has been captured in a single camera. With the help of this NERF, or commonly called as neural rendering, we propose the concept of parameterized communication for 3D video conferencing. Instead of streaming multiple videos for volumetric fusion on the receiver side, we capture a face with a single camera, extract a compact set of parameters, send just those of few numbers, decode them on the receiver, and finally render the frame. Here's a closer look how the neural rendering-based 3D face model works. For every pixel I, j, we shoot a ray through the face volume and sample k points along that ray. Each point's 3D coordinates and view direction angles are concatenated with a transmitted phase parameter eta, and then passed through a lightweight MLP. This single forward pass returns a color CK and density sigma K. Using the volume rendering method shown on the right, we accumulate those output pairs into a final pixel value large Ci, j. And we perform the same procedure for every pixel across the entire image plane. However, we have 2 strict timing goals on immersive communications. The first is to generate each frame in 33 milliseconds. When running previous neural rendering method on a JASA mobile platform, we attain only 2.8 frames per second for 512 size resolution at most, and still fails even if we cut the image size into half. Moreover, when the viewer moves, we have to re-render the frame in 16 milliseconds time budget. This re-rendering process includes to resample the rays, run the MLP, composite the results, and do the super resolution. With the previous approaches, that whole chain takes 137 milliseconds at least, far much exceeding what we need. Here, we can easily figure out that the repeated rate marching persist of previous method is the critical bottleneck. To smash the stringent timing wall of responsiveness, we remove the rate marching loop entirely from the system. Instead of sampling dozens of points on the ray, we treat the pixel as a unit sphere and map their RGB values with each corresponding direction, theta and phi. By doing so, a simple dot product on the pixel replaces all the point sampling and MMP inferences across the ray. As a result, this single step cuts the re-rendering latency by an order of magnitude on the mobile hardware. But the simple spherical harmonics layer looks too flat, so we decide to superimpose multiple layers and blend them with certain weights to bring the depth back in. Here's how it works. We create 3 extra virtual viewpoints with simple geometry rules, and we produce total 4 RGB layers and corresponding 4 spherical harmonics coefficient matrices. For each viewpoint, a single matrix multiply gives the viewing direction for every pixel. Then each layer attains a density score from a spherical harmonics-based linear combination. We soft blend these 4 layers with the scores, finally recovering realistic depth and shading while staying lightweight. This procedure is briefly shown as the figure in the bottom, and we call it truncated rate marching. Now let's compare the computational demand between the previous ones and our novel approach. A classic NERF-style pipeline traces 96 samples for every ray across a 256 size image plane and runs 25K multiply accumulates MLP at each sample, which multiplies out to roughly 155 billion multiply accumulates per frame. In contrast, our truncated rate marching design renders a full resolution of 512 size image by superimposing 4 lightweight harmonic layers and just 16 basis functions at about 3 multiply accumulates each, so the entire frame costs only about 50 million multiply accumulates, slashing computation by an order of magnitude. With the frame renderer complete, our next task is to build the phase parameter encoder and decoder. We choose our encoder to be relying on the expression blend shapes. We adopt an off-the-shelf phase detection module to extract the parameter as a compact set, and the decoder expands those coefficients into the tensor format required by the following renderer. To keep the reconstruction in sync with desired lighting and background changes, we insert a spade block that fuses the decoded features with a reference frame. We call this mechanism style injection or style semantic integration, where style refers to the visual context provided by that reference frame. Now here's the end-to-end view of our system Empilo. First, you can see in the left bottom, each user has his own learned personal profile that is preloaded on the viewer side. We train this small tensor so that each matrix can be scaled by the blend shape values we send. And we also trained the next module called style injection individually for each user, so it matches that person's lightings and backgrounds. The following module, the harmonic decoder, is shared across all users, but thereby keeping it universal. And also, one thing worth mentioning is that our system transmits only 50 floating point numbers per frame, which requires extremely low bandwidth in network. And then the computation-friendly speaker harmonic-based renderer contains no learnable weights at all, as we've gone through the previous slides. We implemented the whole system on PyTorch with the use of half-precision floating points and with the optimization of TensorRT provided by PyTorch. Now let's look at Empilo's end-to-end performance on mobile platforms. We ran the full sender-to-receiver pipeline on NVIDIA Jetson, Xavier AGX, and on a Galaxy S24 Ultra. Recall that we need under 33 milliseconds to generate a single frame and sub 60 milliseconds to re-render when the viewer moves. This bar charts at the top break latency and computations into 4 stages. Particularly with Jetson, the whole receiver side, expression blending, style injection, harmonic decoding, and the lightweight renderer adds up to 30.5 milliseconds. Based on the results, we can find out that Empilo, especially Empilo on Jetson, is the only point that lands in the orange compliant box, while everything in the white zone fails both deadlines. Next, visual quality. We compared Empilo with 2 different paradigms. Against the neural baselines, Empilo matches Nerface's best perceptual score, but renders at 32 frames per second instead of on acceptable rates, thanks to our lightweight pipeline. We then fixed the traditional 2D codecs to Empilo's minimal 24K bits per second bandwidth budget and measured reconstruction quality. All 3 these 2D codecs show visible blocking artifacts as shown, and their quantitative scores also conform higher perceptual loss than our approach. And to summarize, the result of the visual experiment proves that our system Empilo preserves facial detail, avoids the compression artifacts shown in 2D codecs, and most importantly, still runs in real time. And more, we evaluate two advanced capabilities of Empilo. Our system can generate arbitrary head poses, turning left, right, or any other poses, while better preserving identity and expression than the 2 baseline shows, LP3D and PVR. In addition, experiments prove that the style injection module effectively reflects lighting and background onto every new pose when we feed a wanted reference frame. For the last of the evaluation, we have checked PSNR for reconstruction of the scenes inside and outside the training video. The result is that the more diverse the data, the better Empilo generalizes, unlike previous models such as Insta and Point Avatar. To wrap up, here are the key points. Takeaways. Empilo shows that mobile 3D video conferencing is possible by sending a tiny set of parameters instead of visual data. We have introduced 2 new ideas: truncated remarching for speed rendering and style semantic integration for realistic lighting. But our limitations are that the bandwidth is still fixed, so the system does not yet adapt to network fluctuations, and the decoder is partially personalized, so each participant needs a small pre-trained model each. So our next step is to realize immersive multi-party telepresence. We aim to parallelize rendering for many users and to give extra detail to active speaker, so then finally overcome the long-standing issues in the multi-party communication field. Thank you. I'm happy to take questions.
Thank you.
Okay, very interesting work. And this is Leming from Hong Kong PolyU. I have a small question. So, in your system, you only consider that the phase is required to be parameterized and transmitted to the other side. Okay. So at first I thought you parameterized the entire scene and transmit the parameters. So I first thought it can be combined with the first presentation. Maybe we can parameterize the entire thing, and the network bandwidth can be significantly reduced. Okay, it's okay. Thank you very much.
Yeah, I believe it will be on our future work. If you want to generalize the scene or the whole body, then the dedicated encoder should be designed and the dedicated encoder should be trained. So that was not our focus mainly. We prove our concept as in the focusing on the face firstly, and that will be our future work.
Okay, I think your idea is very interesting. Thank you very much.
Thank you.
Thank you for your presentation. My name is Chan Young-jung from Yonsei University, South Korea. So I have a question that can your system also handle the dynamic conditions of mobile platforms such as thermal throttling, or if the device heats up, then maybe the performance of device can be slowed down. So can this system also handle?
Yeah, that would be the main point. In our system, we fully use the GPU and CPU and memory bandwidth to optimize them. Parallelize the process will be the critical, the limitation, or what we have to do in the next research. Yeah, that is a great question.
Okay, thank you.
Can I squeeze in one tiny question? You mentioned, maybe also follow up with the first question. You're focusing on the face, I understand, but the background still matters. It still shows up, and there might be dynamism there. There might be different environments where the same person to whom you've personalized moves. Does your system still work in those contexts if the background changes?
Yes, we proved with the background changes. The previous works doesn't have that kind of function, injecting styles or backgrounds, but we do have the function. I think that is a critical big pillar of our system, mainly. Yeah.
Very cool. Thank you so much.
Thank you.
Let's thank the speaker once again.